Hello, hello. How's everybody today? Doing good, doing good. All right. Well, we are on to our day 3 of Unit 7, so our third day in Calc BC. And remember, this whole unit is about learning new and more advanced techniques of integration. So we've already had 2 days of it, which was all integration by parts and the different types of problems you can do with that. In this day 3, we're going to be talking about some trig identities that you need to know, and just some more advanced trig integrals using some of these identities. I got like 4 types of problems that we can see with this. Okay. So anyway, here's some identities that we should probably know. More importantly, probably uh, these two. We've used these two before already: sine squared and cosine squared identities. It's very helpful for reducing down your power from a squared to no squared term. So these are actually called power reduction IDs. Okay, so you definitely need to know those two. We'll note those two. The next two are cool and all, but we don't use this as much. I mean, we use sine of 2x sometimes, but you probably learned this in pre-calc. We don't use this as much. Same thing with this one. We don't use as much. We hardly ever use that. And the bottom 3 we hardly use as well. But if we ever do use it, the identity is usually given. So if I had to really, star the ones we use, it's these first 2, and then this one right here, tan squared equals secant squared minus 1. That's just an application of the Pythagorean identity, which is cosine squared x plus sine squared x equals 1. And another one that we could possibly use is cotangent squared x plus 1 equals cosecant squared x. All 3 of those are from the Pythagorean identity. So yeah, I'd probably know those 3 and know the 2 at the top. And I think that'll be good enough for all the trig type problems that you'll see. All right, well, let's look at an example of something that would use one of these identities and how we can manipulate a problem using these identities. All right, so here we got the integral of sine cubed. Okay. I mean, if you want to rewrite it like this, you can, just to make sure you see it the right way. But this is sine cubed dx. And there's no u sub we could do. We could do the whole list if you want to. There's no u sub. I mean, you can't. If you let u be sine, du's cosine, that doesn't help. We can't do integration by parts. There's really nothing much we can do there. But we can use an identity, and this is what I would recommend, and you're going to see this pattern today. If there's any time there's a sine or cosine or tan, any trig with a power of 3 or more, you can write it as a product of a bunch of trig functions. So, for instance, like I would rewrite this as the integral of sine squared x times sine of x dx. That's how I'd rewrite this. Okay? Because the idea is to get it down to a sine identity. Okay. We know that sine squared is the same thing as 1 minus cosine squared of x. Right? I mean, remember the identity I just showed you. Cosine squared x plus sine squared x equals 1. So sine squared x equals 1 minus cosine squared x. So all I'm doing is just using an identity and plugging that in for sine squared, and I'm left with sine of x dx. Now, that may look more complicated than what I really started with, but this is really nice for us because if you ever get in this situation where you have a cosine and a sine, u substitution is going to work, right? The derivative of one is the other. So I think the best bet in this case, and you can try it on your own if you want, I think that if we let u be cosine of x, yeah, it works out pretty good for us. Then du would be derivative cosine is negative sine of x dx. And here's the sine of x, and here's dx. The only thing is that the negative is going to come out on the outside. So this works out pretty good for us. We got negative on the outside, 1 minus, instead of cosine, it's u squared. So put that in parentheses. And then the sine of x dx just becomes du. Okay. So that's not a terrible thing to integrate, right? We can integrate this all day long. We got negative. Integration of 1 would just be u. And the integration of u squared is 1/3 u cubed. Right? And then plus c. And then plugging back in what u was, which was cosine, we have negative cosine of x. I'm just going to distribute the negative and make it plus 1/3 cosine cubed x plus c. So that wasn't the worst thing in the world, right? I mean, all we did was just kind of break up the powers and use an identity, and that's the goal of today. Okay. All right. Well, you're going to see in the next 3 or 4 problems specific patterns that you're going to recognize, problems that look very similar. So what I did is I've gone ahead and I've broken down those 4 types of problems that you'll see and the strategies to approach them. Okay, you're going to notice that a lot of times it's going to be the product of 2 trig numbers at a higher degree. And that's kind of what I'd say. So let me write that down for you. It's going to be, you're going to notice the pattern is the product of higher power trig. Now, I give you a list of precedents that makes your life a little bit easier, like in the order that's probably the easiest. So for instance, if you have a sine or cosine with an odd power, okay, that's kind of like the first thing you look for, is sine or cosine with an odd power. And if that's the case, then you're going to use sine squared x plus cosine squared x equals 1. You're going to use this identity and do u sub. And if you think about it, this is the exact example that we just did. Sine cubed, we did the Pythagorean theorem and did u sub. Okay. Now, if that's not the case, if you don't have this situation, but if you have a sine or cosine with an even power, okay, you're going to use your power reduction IDs from the first slide to expand and integrate each item. Okay, so we're going to do an example of number 2 in a second as well. So we've already done an example of number 1. We're going to do an example of number 2. Now, if you don't have either one of those, if you have instead an even secant power, okay, the ID you're going to end up using as part of the Pythagorean identity, it's secant squared of x minus 1 equals tan of x. And you're eventually going to do u sub, and u is going to be tan. So you're going to see how that works in a second. Or the last thing you could have is an odd tangent power. Then you're going to use you're going to still use the same Pythagorean identity, but instead of u being tan, u is going to be secant. So if you haven't already, pause the video and write down these steps, because this is the steps you're going to be referring to when you're doing these types of trig problems. Everybody wrote it down yet? All right, I'm assuming everybody has. Okay. Going on. So, specific pattern you're going to recognize here is the integral of 2 trig functions being multiplied together, and they're higher degree trig functions. So, if you run across this, I gave you 4 strategies to consider. And I promise you, if you stick with the precedence or the order of those strategies, you're picking the easier methods. Okay? So go down the list. Start off with odd trig, so odd sine or cosine, even sine or cosine, as our first 2 strategies. Which one's this? It looks like I do have an odd cosine. So indeed, I can do that strategy number 1. So if you think about it, that strategy number 1, my suggestion was to do u substitution with the Pythagorean identity. All right, well, let me show you exactly what I mean and how you're going to do it. look at the odd cosine that you just did. I want you to rewrite that, okay? Rewrite that as sine to the fourth of x cosine to the fourth of x times cosine of x dx. So if you ever have an odd sine or cosine, the idea is to take out one of those sines or cosines, whichever one's the odd one. You take out one of it to make it even. Okay. So the cool thing is that this one you took out, this is going to end up being my du. You'll see what I mean here in a second. Okay. So if this is going to end up being du, we need to have everything in terms of sine. Okay. So just trust me when I'm saying this. So I already got sine of the fourth here. That's good. I want to rewrite cosine as cosine squared x squared. So let's just recap here real quick. If it's an odd sine or cosine, you take out one of those powers to make it even. And this right here is going to end up being your du. So we'll go ahead and write that. Du is going to end up being cosine of x dx. Just keep that in mind. That's how we're setting this up. So if that's the case, that means u needs to be sine, so everything else needs to be in terms of sine. So this is sine to the fourth of x. The reason I wrote cosine 4 as cosine squared is because cosine squared is the same thing as 1 minus sine squared x squared times cosine of x dx. All right, now I can do that u substitution. Okay, let u be sine of x. Now notice what's going to happen. We're going to let u be sine of x. Then du is going to be what I intended it to be. I wanted it to be cosine of x dx. So now this substitutes out as du, and it's going to be a nice integral for us to solve. So u to the fourth, 1 minus u squared du. Okay. So that's what happens whenever you have an odd sine or cosine. You take out one of the powers, and that's going to end up being your du. You got to get everything else in terms of the other trig function. All right, now this is just a polynomial to solve. I think we should FOIL this. So we have u to the fourth. That's, let's see, 1 minus 2u squared plus u to the fourth du. We can distribute the u to the fourth. So we got u to the fourth minus 2u to the sixth plus u to the eighth du, and then that's just power rules, right? So that's 1/5 u to the fifth, and I'm going to go ahead and write in what u was. U was sine, so I'm going to say 1/5 sine to the fifth minus plus 1 is 7, so that's 2/7 u to the seventh, or sine to the seventh, plus 1/9 u to the ninth, but instead of 9, I'm going to say instead of u, I'm going to say sine 9 of x plus c. All right, there you go. So there's your pattern. If it is an odd, okay, if it is an odd sine or cosine, pull one of them out to be your du, and you're going to manipulate the rest of that to be the other trig function. So if I brought cosine out, I want to get everything else in terms of sine. That way I can do my u substitution. Okay, good. Okay, now in this next one, go down the list. Do we have an odd sine or cosine? No. Do we have an even sine or cosine? Yes. Sine to the fourth of x is the only thing we have. All right, now in this case, I told you we're going to do power reduction. So if we're going to do power reduction, we need to have a sine squared in order to do power reduction. So you need to rewrite this as sine squared of x to whatever power is left over. So in this case, squared. Okay. So anytime you have an even degree, you always want to write it as sine or cosine squared to whatever power is left over. And now you can do the power reduction for sine squared. Remember that identity was 1/2 1 minus cosine of 2x. Okay. So instead of sine squared, I'm going to have 1/2 1 minus cosine of 2x And all of that, let me make sure I didn't write it in parentheses here. All of that is squared. Okay. Now, whenever you do the power reduction, you're able to integrate this. Now, it's going to take a little bit of work, but I think we can handle it. Okay. But again, that's the identity that we use here. Okay. All right. First off, we have this quantity squared, this quantity squared. Let's go ahead and square the 1/2 and bring it out of the fraction or out of the integral. So 1/2 squared is 1/4. So I'm going to have 1/4 out of the integral, and I'm left with 1 minus cosine of 2x all squared. Okay. And now it's just going to be a matter of how we simplify and how we integrate. Okay, so let's go ahead and FOIL everything out. So we can do like 1 minus 2 cosine of 2x plus cosine squared of 2x. All right, so we have this this 3-term thing we're trying to integrate here. We're able to integrate 1, no problem. We're able to integrate 2 cosine of 2x, no problem. Might have trouble integrating this. Okay, so let's go ahead and integrate the other 2 pieces real quick, and then we'll be set. Okay, so I got the 1/4 on the outside. And I'm going to be distributing it as I integrate. So the integration of 1 is just x. So I got 1/4 x. Now the integration of -2 cosine of 2x. So let's think about this. I'm going to put a minus here. Let's think about what the integration of cosine of 2x is. We can do u sub if you want, but remember, all it's going to happen is a 1/2 is going to come out. And the 1/2 is going to cancel out the 2. So really it's just the integration of cosine of 2x is sine of 2x. So this is going to be minus, the 1/4 is coming through, 1/4 sine of 2x, right? Because when I integrated the 2x, it got rid of the 2, all right, but remember the 1/4 is still coming through. And then we're left with the integral, or 1/4 of the integral, I apologize, the 1/4 is distributing through. We're left with 1/4 the integral of cosine squared of 2x dx. Okay. Well, if you notice, we have an even cosine function, so we're going to have to do power reduction again. All right. So let's go ahead and rewrite everything out. We got 1/4 x minus 1/4 sine of 2x plus 1/4. Now the power reduction for this, if you remember, was 1/2. Okay, 1 instead of minus, it's plus cosine of 2 times the quantity, so that would be 4x instead of 2x. All right, now I'm probably going to bring the 1/2 out again, and then I can integrate 1, and I can integrate cosine of 4x. Let's go ahead and do this. So we got 1/4 x minus 1/4 sine of 2x plus 1/8, okay, times the integral of 1 is x. Okay, the integral of 1 is x. And the integral of cosine of 4x is going to be 1/4 the sine of 4x. Remember, the 4x just comes out as a 4, or 1/4, plus c. Now, I'm okay with you leaving it this way, but if you want to combine like terms, you can. I'll just do it this way. I'll just make it. Honestly, you can leave it the step before, but I'll distribute the 1/8. Why not? So how about 1/8 x plus 1/32 sine of 4x. Now at least everything's distributed, plus c. So the big thing to take away from here, even sine or cosine, you use power reduction. Now we got two more. Let's look at this one, okay? We've already done, okay, so we go down the list. We don't have an odd sine or cosine. We don't have an even sine or cosine. The next two are even secant or odd tangent. Now I realize we have both. We have an even secant and we have an odd tangent. So you could do either strategy 3 or 4 for this one. It's fine, you can. But strategy 3 is a simpler process than strategy 4. So if I had the option to pick, I would go with the even secant. Right? If you had the option to pick between tan, an odd tan, and the even secant, I always go with the even secant. Okay? Now, if that's the case, this is how I want you to rewrite it. It's very similar to doing strategy 1. We're going to have the integration of tan 5x, okay? And I want you to rewrite this as secant squared x times secant squared x dx, because this is going to end up being our du. Because remember what I said u is going to be in these problems. U is going to be tan of x, and du would be the derivative secant squared x dx. So I got the du right there. And if I want to make my u tan, I need to have everything else as a tan. I got tan to the 5th here. I need to rewrite secant squared in terms of something with tan. Well, I have an identity for that from slide 1, if you remember. This is the integration of tan to the 5th x. Secant squared is the same thing as 1 plus tan squared of x. And I'm left with this secant squared x dx. So notice, this strategy is very similar to strategy 1. You're pulling out something. Instead of pulling out one sine or one cosine, with an even secant, you're pulling out two secants. So your du would be secant squared. So now, if I were to do u substitution, it's going to work out really nice for me. I'm going to let u be, like I said earlier, tan of x. Du is secant squared x dx. Everything substitutes out nicely. This becomes du. Everything and all those tans become u. So I got the integral of u to the 5th, 1 plus u squared du. And I can integrate this all day long. It's polynomial. U to the 5th plus u to the 7th. And those are two polynomials that I can quickly take the derivative of. 1/6 u to the 6th plus 1/8 u to the 8th plus c, and I can go ahead and substitute back in what u was. So that's 1/6 tan to the 6x plus 1/8 tan to the 8x plus c. Now, if you really want to, you can try to do this the other way around. You could do it with an odd tan strategy if you want, but the process is going to be longer. Your answer will look different, but they will be equivalent equations. I think it will be in terms of secant instead of tan, but this process makes it a lot easier. Okay. So again, took out the secant squared and made that my du, so I got everything else in tan. It was a nice little problem. Okay, only got one more for you. We'll be done. That's the last strategy. So if you notice right here, I got no sine or cosine that's odd or even, and I don't have an even secant. The only thing I have is an odd tangent. Now this is the longer of all the processes, but it's not the hardest. It's not even the longest sometimes. It's just the last strategy I pick. And sometimes it requires us using these integrals over here on the right that I put in this box. So that's why it's the last strategy, because I don't require you to memorize the integral of tan and the integral of secant. And it's not a requirement for the AP exam. If they're ever needed, they give that to you. So I just wanted to let you know. But this is the basic strategy of this. Okay, if you look back at the strategy, the idea is that I want my du to be secant x tan x dx, because I want my u to be secant x. So if that's the case, I'm trying to take out my du like I've been doing with all my other strategies. Okay? So that means I need to take out one secant and one tangent from each of these powers. So what I'm left with is tan to the fourth x, secant to the 6x, and I'm pulling out that du as secant x tan x dx. I just pulled out one power, so this will end up being my du. Now, if that's the case, I need to get everything in terms of secant. Well, I got secant to the 6 right here. I got to get something plugged in for tan that's equivalent to secant. Well, again, all it is just an application of the Pythagorean identity. I can't do it for tan to the fourth, but if I rewrite this as tan squared x squared, secant 6x times secant x tan x, then I can use Pythagorean identity. I know what tan squared is equal to, right? Based off of Pythagorean identity, tan squared is the same thing as secant squared x minus 1. But there you go. Like, we got our du right here, and we got everything else in terms of secant. So do your u substitution. So I'm going to let u be secant of x, and du is going to be secant x tan x dx. Okay, so what I have circled here becomes my du. Everywhere I see a secant, I'm going to plug a u in, so that's u squared minus 1 squared times u to the 6th du. And this is beautiful. This is just a polynomial that I can simplify and integrate. If I were to FOIL, that's u to the 4th plus 2, or 2u squared plus 1 times u to the 6th. And I can distribute that u through as u to the 10th minus 2u to the 8th plus u to the 6th du. And it's just 3 power rules that are pretty straightforward. So that's 1 over 11 u to the 11th minus 2/9 u to the 9th plus 1/7 u to the 7th plus c. And remember that u was just secant. X minus 2/9 secant 9 plus 1/7 secant 7x plus. And there you have it. That's it. Okay. So with a couple minutes left over, let's just recap here. We thankfully ended up not needing these integrals here, so that worked out pretty dang good for us. But sometimes they do pop up. And I've seen them pop up with these types of problems. So just keep those kind of in the corner of your notes in case that issue ever does run up. But just to recap, our 4 strategies. First strategy was an odd sine or cosine. The idea was to pull out the one of the odd powers to make it even. Okay, and then we just do Pythagorean identity. Pythagorean identity to get it as the other trig function, and then do u substitution. Okay, so that's strategy 1. Strategy 2 was to take an even sine or cosine function, rewrite it as whatever that function squared to the remaining power left over, and then do power reduction. I think strategy 2 is a little bit difficult as regards to the other 3 because it's a little bit unique. But once you do power reduction, it's all about just simplifying this down as much as you can and integrating each piece. Unfortunately, in this problem, we just had to do power reduction twice. Okay. And the last 2 strategies are very similar to the first strategy. Okay, so if it is an even secant, you pull out the secant squared, and that's going to be your du. Everything else needs to be in terms of tan, and that's using the Pythagorean identity. And it's the same thing if you had an odd tangent. Okay? If you had an odd tangent, you're going to make your du secant and tan, So you're going to pull out a secant and a tan and get everything else in terms of secant. So you can do unit substitution. Okay. So strategy 1, 3, and 4 are very similar. Strategy 2 is a little unique. But try you some practice. Try you these problems. Okay, you got examples of all of them. Answers are always uploaded. So I know I'm not here with you today, but here's your practice. And if you can do these, you're doing just fine. Okay. Otherwise, I will recap all this as much as I can to make sure we are all prepared, and life will be great. So we'll do a smiley, heart, star. Oh, that was awful. Okay, I'm gonna end the video there. Goodbye.